Good afternoon, everyone. I would like to start by just thanking the GNU Radio Foundation and Ben for setting up this awesome conference for all of us to get together and share ideas, new developments, collaborate on things. One thing that you kind of get going towards the end of a conference is you get to feel sort of what people are interested in. You get to see where they want to get to and potentially how they want to get there. And one theme that I kind of picked up on throughout this conference was this idea of heterogeneous processing, right? So this idea of taking your algorithm and its different pieces and parts and throwing any type of hardware that you could think of to optimally run that particular block. And potentially just shuffling those blocks all around as well, painlessly. So a little bit about me. My name's David Pocratsky. I work for a subsidiary of Boeing called Boeing Intelligence Analytics. I'm an embedded software engineer, and I've been working on this integration of OpenCPI and GNU Radio for the past 4 or 6 months or so. And that's what I'm here to tell you about today. So just before we start, can I get a show of hands of FPGA developers out here? Okay. How about software developers that want to use FPGAs but don't know how? Okay. This is what this presentation will be very interesting to you. So there's 3 things I want you to get out of this presentation, and if I can express those ideas, I've been successful in my job. The first one is I want you to know what OpenCPI is at a slightly deeper than surface level. So just be able to explain what it is. The second thing is what we're doing with GRC right now. And the third thing is how to get more information. And I'm going to go, that's the different pieces of my presentation are laid out in that way. So this first section, I'm going to do some explanation of OpenCPI. What is it? Because I'm guessing most of you probably don't know what it is. And then what we're actually doing with GRC, and then how to get more information. So OpenCPI stands for Open Component Portability Infrastructure. Basically what it is a framework that allows you to, it's a component-based framework. You use your components to build applications in a homogeneous way. So your component is going to be some abstract definition of a part of an algorithm, and then you have different implementations of that for different paradigms of programming. So like hardware, FPGA development, software, potentially GPUs. And the OpenCPI framework just handles all of the communication between them for you and the switching and the deployment of your application for you. And from the ground up, this has been designed to be platform agnostic. So this is the open source solution kind of for homogeneous processing. If there's a new programming paradigm that happens to come about, this can support that as well, as long as once it's ported to OpenCPI. So visually, what does an OpenCPI application look like? It's very similar to GNU Radio, actually. You define your blocks, and then you use those blocks to build your application. And then there's one extra step where you take your application and say how you want to run it. So right now, GNU Radio and GRC, everything's running pretty much in the processor. There's some one-off things where you can kind of put things in the FPGA, perhaps. But for the most part, they're just in the processor, your x86 CPU or embedded processor, if you're cross-compiling. So you build your blocks, build your application, and then deploy them to some set of hardware. So this next section, I'm going to kind of go over some terminology of OpenCPI, because there's a lot of similar ideas that are called different things in different frameworks, and there's a lot of similar names for things in different frameworks. So I just want to establish a baseline knowledge for the verbiage I'm going to use. So at the top level, you have your application, which is synonymous with a GRC flow graph or GNU radio flow graph. It's your set of connected up blocks. And a combination of component and worker is what is considered a block in GNU radio. So this is where things start to get different. So in order to do this this homogeneous processing, we had to create a new abstraction layer. And that's what we call a component. So this component is your abstract definition of what your algorithm is going to do and define your ins and outs for it. And then your specific implementations of that abstract interface is going to be your worker. So you could have, let's say, a fur filter component and then an FPGA implementation fur filter worker, or a ARM processor or RCC software worker, sorry. Okay, so we have applications that are made out of components that are implemented by workers. The next layer out is a container, and I won't go too much into this. It's actually much more detailed than this, but for this presentation, just know that a container is some type of execution environment. It's another layer that we needed to do in order to be able to move one component from one to another. So then each of those containers are housed in physical hardware, which is what we call a platform. So a platform could be a general purpose processor, it could be a GPU, it might be an ARM processor, it could be an FPGA. And then the way FPGAs are kind of special in that you can only program them once, pretty much, ignoring partial reconfiguration. So there's one extra step we have to do for FPGAs. If you build components that are running in one FPGA, so they're co-located on one platform, there's one extra step of building what we call the assembly. And that's essentially your bit file that is going to be used to program the FPGA. So then you have all your interconnects, and OpenCPI handles all of this for you, so I'm not going to spare too much on this. And then everything together is called the OpenCPI system. So you have your OpenCPI system that has lots of platforms that are interconnected, that have containers that run workers that are defined by your application, made up of interconnected components. So what can we do with all of this? Actually, how am I on time? Did we start early? Okay, cool. So I'm going to go into a couple differences of existing frameworks. So this is just a real high-level slide. I think, so for GNU Radio, obviously it's not currently targeting hardware, FPGAs, vanilla GNU Radio. RFNOC kind of adds that in, but it still doesn't really target GPUs, and it's kind of vendor locked. OpenCL is similar to OpenCPI, but it has a different philosophy in how it's trying to solve the problem. OpenCL's philosophy is one language to rule them all. It wants to write everything in their math kernels and use that to translate the kernel to whatever native language or bit file that it needs to program. OpenCPI is kind of different in that we're not out to solve that problem, or even if it is a problem to solve, we want the years of development of that language for that particular platform to be taken advantage of, so we allow you to do that. So we're not going to try to have a one-size-fits-all language. If you're programming an FPGA, use VHDL. Red Hawk, also kind of another similar thing. The way I've had it described to me as the difference between OpenCPI and Red Hawk is more for like big server-based applications. You have a room full racks of servers and you want to run some really high processing thing on all of them, Red Hawk is the tool to do that. OpenCPI is kind of the last mile of a marathon, if you will. OpenCPI targets more embedded processors, FPGAs, smaller networks of things. So that's kind of a one-sentence description of how all of these things kind of differ. And that summarizes, that's going to cap that learning section. Yes?
I just wanted to differ on RFNOC
Sure.
being distributed.
Sorry, Matt, can you get a mic?
So I will preface this slide with I'm not an expert in any of the other ones, so
Yeah, no
if
no
there's
problem.
a clarification,
I just want to
appreciate
say one of the key design goals of RFNOC was to be distributed, and it does work across multiple FPGAs and processors.
Okay.
The DARPA Coliseum system for Spectrum Challenge actually has 192 FPGAs in it that are working together.
Nice. Okay. So this needs some updating, obviously. Things move pretty quickly. So I think I was talking to some of the Red Hawk guys yesterday, and they said they're working on GPU support. So things move very quickly. Sorry about that. So hopefully you can have a surface level view, slightly deeper than surface level view of OpenCPI, and be able to describe it. So what are we doing with GRC? Well, we've done a lot of the core runtime work for OpenCPI, and we're kind of getting to that point where we need to be able to enable this runtime to our application developers in order for them to solve problems, just like GRC is for the GNU radio runtime. And we saw that parallelism, and we thought, hey, wouldn't it be awesome if we could just take advantage of all the work that GRC has already done and use it for OpenCPI? And there's two ways we'll benefit from that. One is we'll benefit because we get to take advantage of all of the cool GUI, frequency and time sinks, and signal analyst tools, plus all of the software workers that have already been written in GNU Radio. And GNU Radio will be able to take advantage of the work that we're doing by running on FPGAs, running on GPUs, running on embedded processors, things like that. So that was the motivation for our integration with GRC. So what I'm going to do now is move into a demo portion and kind of live demo show what we have working so far. This is an outline for what I'm going to show. So the first thing you need to do is install OpenCPI and build all of the assets for your desired platforms. And you'll probably need to write your own OpenCPI workers specific to your application. I'm not going to show that. There's tons of documentation on that, which I'll link to on my last slide on our GitHub. But where I'll pick up is we wrote a tool that translates OpenCPI XML into GRC XML blocks. And that's kind of our entry point into using the GRC for building OpenCPI applications. Once you have those, you can create a flow graph just as you normally would with OpenCPI blocks. You can then set the deployment to where you want them to run. And that's a new step versus vanilla GRC. And then you just build and run the application, and it handles all of the work for you, all the hard work. So this first step, this OCPI GR tool, I'm not going to spend too much time on this. You basically point it to whatever workers you have written or built. You point it to that, and you run the tool, and you say where you want the blocks to end up. And it's usually pointed to where GNU Radio is installed, unless you have some specific place where you have your blocks. And instead of going through the slides, I'm going to attempt Murphy's Law and pull up our version of GRC. So the first thing you probably notice is these are colored. That's different. What these colors represent is, actually I'll take a step back. So after you run that OCPI GR tool, you'll now have an OpenCPI block tree over here on the right. And you can interact with that just as you can with any other block tree, any other GNU radio blocks. So you can open up files or pull in blocks, connect them up, do the same things you're used to doing. There's no new learning here. So what I have here is a BFSK application that's reading in a bit file, doing the symbol mapping and zero padding, pulse shaping, modulation, and I'm writing that out to a socket. And a BFSK is just one frequency for a 0, another frequency for a 1. So nothing new, just a good example to show that this can actually do some work. So going back to the colors, so each OpenCPI block has a container that says where you want to run that part of your algorithm. So for this application, I have the file read on my CPU going into a series of blocks that are currently running in simulator, XSim. So I've Auto installed on this laptop. I'm using XSim to run these blocks, and then I'm writing that out to a socket. And whenever I generate this, we auto-detect that there's an OpenCPI block that's in this flow graph, and we override the typical GRC generator. So usually your flow graph would get translated into Python and use the GNU Radio runtime to run your application. Since the GNU Radio runtime doesn't really solve this use case for us, we're kind of circumventing that by converting it into our own application XML files and using the OpenCPI runtime to run our application. So I can generate that, I could run it, and it's going to kick off the simulator. You'll see some output down here. I'm going to jump over to this other GRC flow graph that I've written, which is the inverse of the modulation I have on this flow graph. So this is using vanilla GRC blocks, and we see that the simulator has started up and it's listening for a connection. So I'm reading from that socket that I'm writing to at the end, doing the demod and piping that out to some output. And we can run that and it'll connect up, and as soon as the simulator decides to run a little bit faster, it will output some data. So that's cool, but that's not really the interesting part of this. That's not really empowering. It doesn't allow you to do anything. What we can do, and what OpenCPI gets you is, I don't know if you probably haven't seen, but I have a Matchstick Z1 under here connected to my laptop with Ethernet. So let's say I'm moving from the development phase where I'm running in a simulator, running on my local computer. Now I'm moving to a deployment phase where I'm actually deploying on the Matchstick. All I need to do is switch the container that these are set to, just set the deployment to be the Matchstick. So for each of these blocks, you can go in and change them, and I can use the shortcut in GRC to be able to set the container to run on the Matchstick's ARM processor and the Matchstick's actual VHDL logic. So all I need to do is generate that, and I have a terminal open on the Matchstick here, kind of already set up for me, and I can do OCPI run -v and I can run that, and it started up much faster because it doesn't have to deal with the simulator. Go back to my demodulation, point it at the Matchstick, and run it. And it's going to connect up, and you see that it's running much faster. And we're actually getting bit, you can see the bit changes now. And the file I'm sending is actual, it's meaningful, it's not just random ones and zeros. And I have the output of it printed out here as a raster plot. So, yeah, thank you. So let's take a step back and think about what just happened. So in a matter of a few minutes, we ran an application with 2 deployments running on an ARM processor, part of it in the FPGA, part of it in a simulator, part of it on an x86 processor, and both of those deployments talking to a GRC flow graph that was doing the other, essentially the receive side. One thing I kind of glossed over was, I don't know if you noticed, but there's a new button up here called Build. What that does is it'll take your subgraph of your OpenCPI application, and if there's something that needs to be built, it builds it. So I kind of did that ahead of time because it takes a while to build for a matchstick. It takes probably about 30 minutes, and we don't really have time for that. So I did that ahead of time, but it is as simple as just clicking this button to get the artifact you need to be able to run this on an FPGA. So I'm going to bounce back to the slides, because that about wraps up the demo, and I'm going to blow through all these because that's just explaining what I just showed you. So we're not done yet. We have some work still to do, and throughout the slides you probably might have seen the star on like the second slide where it said OpenCL support coming soon, or GPU support coming soon. That's in the lab we have a branch working with OpenCL that uses OpenCL as containers. So those will show up just like any other container. You write your OpenCL kernels to be able to run on a GPU. We have that working in the lab, it just wasn't quite ready for this. Another thing that we're kind of working on is remote deployment. So instead of having to switch from a terminal into, like, say, the matchstick, I would have just been able to hit run. We also have that working in the lab, just wasn't quite vetted out, ready for prime time yet. Should be coming, if not in the next release, the one after that. And one big thing that's missing is the communication from GRC to OpenCPI or OpenCPI to GRC. So instead of having to go through that socket, we want to be able to talk directly. And I don't really know how that needs to work. I think Jonathan might have some input on that. I don't know if he's here. Yes, let's talk. Cool. So yeah, there's some other OpenCPI things that we need to pull into and expose through the GRC. So you might, instead of writing to a socket, we can write to an actual like A to D or D to A, an antenna, actually transmit. We could do that by hand in OpenCPI now. We just haven't exposed that in GRC yet in a way that makes sense, so we're still working on that. And we also need to support more platforms out of the box. So whether that's by us or if we can get support from the hardware vendors, that would be awesome. So how to get more information? We have a opencpi.org website. We have a GitHub. If you do check out the code, make sure you check out the 2017 Q2 branch. And if you're checking out any of this stuff and you have issues, go ahead and email us at issues@opencpi.org. And with that, that's about all I have.
All right, let's thank our speaker. Live demos are, takes courage. All right, do we have any questions? Oh, wow. Okay, Eric, you started.
Yeah, thanks. First of all, I think it's really slick that you're able to run XSIM from GRC. I think that's so you're not waiting. all day to synthesize and, build your image. I think that's really cool. Are you going to get sued for doing that when you try to release the code?
I will have to defer that question to the. So I've done a lot of the work on the integration of OpenCPI and GRC, and our development team mostly is over there. So can we get a mic over there? I might defer some questions to them. So the question was, are we going to be sued? I think the answer is no, but I think we have partnerships with some vendors.
It is a closed source license for all the botted stuff.
So you can use a Webpack license for XSIM.
That's compatible with GPL.
So since XM is not, based on my understanding of what he showed, sorry, I'm going to answer this question for you.
It's fine.
It's because GNU Radio is not actually being linked to XM. it does not become subject to GPL, right? You're just making
Right.
calls out to XM.
Exactly.
Yeah. So there's an IPC barrier there.
We also actually launch all the tools in the background hidden from you. You never have to look at the ISE, the Vivado, the Quartus. You never have to pull up their GUIs again to do what we're doing. And Boeing might have a few more lawyers than Xilinx, so we'll see. No, I don't think it's going to be an issue. I don't think it'll be an issue.
Fighting words. All right. Did your question get answered? Yes. Okay, great. Trip,
Thank
who's
you.
next? I saw like 8 hands go up. We have some down here.
Hi.
Hi.
So, I mean, it was a great demo.
Thank you.
Do you guys are you planning to have support, or I don't know if it already works, but the ability to set properties down to the actual blocks for real-time setting changes?
So
or,
yes,
I mean,
that
variables?
that is able to be done with OpenCPI by hand. I guess I'll call it by hand, not through a GUI or anything.
Okay.
So we have a C++ interface that allows you to control the application both at startup and at runtime, and then you can expose that however you want. I don't know what that's going to look like integrated into here. Probably some type of tie-in with the Qt GUI sliders and things. So it can be done now by hand, and it probably will be easy to do in the future.
Answer your question? Great. Jonathan?
Thank you. I have 2 questions. The first question is, I've been looking at your GitHub repo,
Yeah.
and where is the state of the GitHub code versus what was displayed today? And if it's not the parity, are you going to release that sometime soon?
Yes, so there is some slightly differences with what I showed and what's on GitHub. The GNU Radio stuff is in the process of being pushed. And some of the blocks that I used were also developed with our development team. So I don't know if all of those are out yet or not, or if they will be, but that's kind of the state of things.
Okay, and for the second question, so I love the fact, OpenCPI, open source. How do you see developing a community around it?
We hope that people coming to conferences like this, getting people excited, getting people interested in it, and supporting where we can, building up that community. So the first step in developing that community is bootstrapping it. So once you get enough people that know about the tool, they kind of support themselves. And that's what we're kind of hoping to do, is bootstrap this community of OpenCPI developers so that they can be self-sustaining. So we're going to push the initial effort into getting this adopted.
Thank you.
Thank you.
Oh, Kellen?
So I know you mentioned on the last slide, one of the things on the roadmap is to support more platforms.
Yes.
Right, because there's 3 right now: the Matchstick and the 2 dev boards. Is that still true?
I know we support Matchstick and a ZZipper board.
Okay.
Am I covering them all?
We actually have a handful. There's the Xilinx ML605, which is
Yeah.
a PCI, the Altera ALST4 to show that we're platform agnostic as far as the Xilinx, or the FPGA vendors as well. We have the Z with the zipper card. In development, we have the FMCOMS3. That'll be in the next release, so you can drop the FMCOMS3 onto whatever cards. A lot of the stuff he kind of hand-waved, there's a whole card and slot paradigm where you can say, I have a base card with this slot in it, and then I've got an FMCOMS3 plugged into it, and therefore, you just have to define an XML. Here's where my I2C lines are to go to the 809361.
Okay.
That's part of a board support package
Okay.
that needs to be developed for any platform you're trying to deploy to.
Okay. All right.
Any other questions? No. I actually have one for you. So you talked a little bit about trying to get hardware vendors to build, I guess, the equivalent of board support packages for their devices.
Yeah.
What about supporting other types of processing elements? What does that look like? So you mentioned GPUs, FPGAs, embedded CPUs, GPPs, x86. What about what about DSPs or like NVIDIA's new TensorFlow ASICs and those kinds of things? So what does it take to actually target a different type of processing element?
I'm going to let Aaron handle that question for me.
I'm not really sure. I haven't done it myself. I know at least with the OpenCL stuff, it was pretty straightforward. Basically, because we're handling all the data flow for you, you would have to have it connected into our interconnect. So, for example, porting to a new platform that had a Zinc on it, we already have all the components in place to talk across the AXI bus. We do have variable width bus adapters, so if you're trying to talk to, if whatever the ASIC gives you, if it gives you a 128-bit wide bus, we can take advantage of the 128-bit wide bus automatically, but you would still have to write whatever's needed to talk the internal language that we're switching through the system.
Any other questions? No? Thank you very much.
Thank you.
Okay, we're running a little bit ahead of schedule, so we're going to pause for 5 minutes or so and then actually start at 2 p.m. sharp. And in the meantime, Ben, I know that your talk has a bunch of media. If you want to come get set up so you're ready to go, let's do it.